Good afternoon. Welcome to the second session of the first day of the first ICP workshop on quantum and statistical mechanics. And I'm glad to announce the first speaker of this afternoon, Professor Alexandre Cavalheiros from the Physics Institute of the University of Brasilia. Welcome.
Thanks for the presentation. This presentation today, basically, I like to answer the following question. Can we use 2D carbon allotropes as a solar harvesting for solar harvesting devices? But first, instead of starting answering this question, let's understand why are we interested in that. The same old problem of global warming. Basically, year after year, when we start from 1975 and goes to today, we are reaching the limit of Paris Accord, okay? And if we start in the same progression, we'll reach the second limit sooner. Basically, this is the same idea, but what's happening in Brazil? So we have an enhancement of temperature in the last years above 1.5 degrees. Okay, it doesn't change so much our lives, if you think about that. But for the biomas and the environment, this could be a huge problem. And what causes it? Greenhouse effect. And the majority of greenhouse effect is caused by CO2, carbon dioxide. And the problem is, where it comes, this carbon dioxide? Basically, it comes from fossil fuels. Coal, oil, gas. However, why are you using? Which use did we do for these fossil fuels? A significant part is energy consumption or energy production. So still, year after year, we use more coal, more oil, more gas to produce energy. Of course, this is not the reality of Brazil, but it's the reality of the world. However, in this scenario, we still have hope. So we see some enhancement of the renewable energy, okay? And we see some increasement of solar photovoltaic generation. When we look at the solar energy, we can see that Brazil, for this kind of production, is a very good country. So we have a good solar incidence here in our country that allow us to have a good production of solar energy in the entire country. And that's interesting. Different from Canada or the north of USA or Russia or Europe. So it's really more easier to produce solar energy here due to the situation, the geographic localization of our country. So this is a graph of NRL that shows the evolution of solar devices, solar cells, according in the years. So you can start if it's in 1975 and goes to 2024 here. And we see a huge increment in the solar harvesting efficiency. So imagine that in the 70s we have a small efficiency, for example, 4%, 8%. We have some solar cells based on silicon with 20, 24%, but they are very expensive. It's still expensive today. But we have a lot of new technologies, including organic solar cells. And when the efficiency enhances, the prices lowers. So we can imagine that year after year, this technology is more cheaper, more achievable to use in our homes, or industry, or another applications. In this scenario, our proposal is to investigation 2D carbon allotropes. Why this? First, carbon is the element most abundant in our planet. All life is based on carbon. Other thing, carbon has four valence electrons, and it can achieve several types of chemical bonds. So it can have, for example, graphene, and have these other carbon allotropes. Some of them are semiconductors, some metals, some semi-metals. However, the problem is the majority of carbon allotropes, until we know, are semi-metals or metals. But the majority, not all of them. The most known is diamond, graphite, graphene, fullerenes, carbon nanotubes, okay? But as I told you, the majority of them are metals or semi-metals. What we did in this investigation? First, we start from a 2D carbon allotropes database, okay? We get 13 carbon allotropes, and we select carbon allotropes that shows a semiconductor behavior and has less than 40 atoms. We avoid to get each larger unit cells due to the computation limitations of our laboratory. Only this, only a computation limitation, not in non-physical aspect or anything like that. Okay, so we start with 13 carbon allotropes, and we start performing DFT next function theory simulations. Okay, using Vienna ab initio simulation package. That's a very known DFT package. After this, we get all this entire set of systems, okay, and made phonon simulations. However, as I told, I have system with 14 atoms, and perform phonons in this is very expensive. So we use density function tight binding theory using the FTB plus code. That's a cheaper model, okay, but it still has the majority of properties of first principle calculation, okay, but with some parameterization for carbon that works very well. And we perform phonon calculations and molecular dynamics in order to know if those systems, those allotropes are stable. And stable at room temperature and 400 Kelvin. That is the solar cell temperature operation. After this, when we discover which one are stable, we do the electronic properties characterization, okay? So we perform electronic properties, band structure, band gap, okay? And after this, we goes to the optical and excitonic properties. This part, we use the one-time-axis code, okay? That's a code that we developed here in our university, okay? And we obtain the excitonic properties and optical properties in order to estimate the power conversion efficiency or the solar harvest efficiency of these materials as a single observer in the solar device. In the end, we can identify which one can we use to applications in industry or the academics. So this is our initial set, okay? We have 13 allotropes here. You can see that this one look like graphene, but it's a little different because it's a kind of graphene bilayer, but the carbon-carbon distance between one layer to another is the same carbon-carbon distance in the in-plane graphene, so it's a little difference. However, from the point of view of electronic properties, this guy here is very different from graphene. For example, graphene is a semi-metal. This guy is a semiconductor with 2.1 electron volts of band gap. And we have here another kinds of carbon allotropes here. When we do the stability test, basically we start from phonon frequencies, okay? And we can split our system in three types. What we call stable, all frequencies are real, no imaginary frequencies, okay? We had what we call semi-stable systems. Is that what we have is very small imaginary frequencies, which we expected to be some numerical error of the approximations used, okay? And the unstable systems that we have several imaginary frequencies and this structure is not feasible. The materials that we classify as stable and semi-stable, we perform molecular dynamics. In order to see at two temperatures, okay, 400 Kelvin and 300 Kelvin to see if the system is stable at this temperature, which is the temperature that the solar cell works, okay? And basically what we look is the total energy. If this total energy oscillating around the minimum, this indicates that the system is stable at this temperature. And it doesn't have any phase transition for another carbon allotrope type or new structure during the simulation, which suggests that our systems are stable. All systems that are stable and semi-stable, when we do the molecular dynamics, we see that all of them are stable. Well, this is the set of stable systems. So we start with 13 systems, and now we have 14. Sorry, we start with 30, now we have 14 systems that are stable. What is interesting, when we get from the database, we expect that all of them would be semiconductors. In the first lesson that we had, it's a lie. 2 of them are semi-metal and metal. This one is metal, this one is metal. So really, doesn't trust blindly in a database. Do your calculation and check if what they report is true. Sometimes it's not. Of course, it's also depend of the level of calculation done and limitations of approximations and other stuff, but it's important to be careful with this. So we performed this band structure at PBE level, and after using hybrid exchange correlation functional to correct the band gap. The same old problem of band gap, when you use this GGA exchange correlation functional, the band gap is estimated. So we use hybrid exchange correlation functional to correct the band gap and have estimate better this band gap if one closes to what the experimental would measure or something more real. To do this, we do a little different methodology, okay? To study the excitonic and optical properties, we can use DFT, this functional theory, but this functional theory for excitonic effects is very, very heavy from the computational point of view. So what we did different from the rest of the country and rest of the world. Basically, we use a tight binding model, okay, based on maximally localized linear functions. So basically, we do the FT calculation, and we use a code called Vannier 9, okay? And we can extract directly from the FT a tight binding Hamiltonian. This Hamiltonian is much more simple, but can produce in a good quality when compared with the FT simulation. So this is an example of tungsten selenide, where we have the FT calculation and the Vannier 9 tight binding, and the results from the band structures close to the firm level is basically the same. So what you can see is that we have a good description of electronic band structures around firm level, okay, using this cheaper model. And with this cheaper model, this tight binding based on Vannier functions, we can attack the Beff-Salpeter equation and try to solve the optical properties considering excitonic and without excitonic effects. But first, what is an exton? Basically, exton is a quasi-particle when we have an electron and hole pair bounded by a Coulomb interaction. And okay, but what is the problem of this? Why this is important? What happened is, for 2D materials, those effects are not so smaller than in a bulk. So they can result in a significant redshift in the optical band gap, and also can change significantly the absorption spectrum. So for example, if you get MOS2 was one of the first 2D materials that we see with a band gap. When we try to do the FT simulations, traditional, we have a description of the optical band gap, but when we have experimental measures, our absorption spectrum has non-similarity with the experimental obtained. Basically, 2 peaks that we can see in the experimental measure we didn't see using density function theory. So this revealed that, okay, something is missing. And what we discovered that's missing is exciton, excitonic effects. So this also provides a redshift, but provides two peaks that people call exon A and B that are not described by traditional density function theory. So people start to look for Beth-Salpeter equation to study this in 2D materials. The problem is, if we use this in DFT, you can use YAML code that Professor Venezuela told a few weeks ago. You can use VASP. You can use another codes. This is very expensive. Basically, if you use the computers that we have here in the university, in the physical Institute of Physics, we can't do this simulation. It's simple. We need more than 1 terabyte of RAM memory, at least, to start this simulation. So here in Brazil, it's really difficult, really challenging to do this simulation. Of course, we can't stop the research with this. So one alternative that we found is to attack this problem, this external Hamiltonian, okay? And you use the Beth-Salpeter formalism in the same way as used in DFT, but we treat the kernel, Bessie kernel, okay, the Coulomb interaction, using a tight binding approximation, which is much simple, okay? And the computational cost is at least 1 or 2 orders of magnitude in the computational time. So, for example, if you do this calculation of Beth-Salpeter for MOS2 using YAML or VASP, imagine that it can cost you maybe, I don't know, 3-4 months. We can do this using my code, one type access, in 3-4 minutes. So that's what we are talking. We can have a good enhancement in the computational time, okay? Of course, this approximation have its limitations, but we can have the first results using this, okay? So the theoretical aspects are in those 2 slides, okay? But basically, the equations are the same, but we change how we deal with the Coulomb kernel. And this saves us a lot of computational time. Other thing that's important, excitons are not equal to an electron in a hole separately. So those excitonic effects are very sensitive. So imagine that I have a MOS2, for example, or a carbon allotrope. If I put it suspended in vacuum, I have one optical response. If I deposit it in HPN or another insulator, the optical response will change. Even if the interaction between the 2D material and the substrate is weaker. It's a kind of van der Waals interaction. So this kind of excitonic behavior is very sensitive of the dielectric environment, okay? So that's important because you can use some strategies to try to modeling it, okay? Other thing that you can do is calculate the excitonic band structure. So exons can have a momentum, and the momentum is basically the difference between electron and hole momentum, okay? And we can calculate it, solving Beth-Salpeter equation. The problem is that this calculation is very expensive, but using one-type Exos code, it's okay to do. You can do this in 1 day instead of 1 year. And we can identify direct excitons and indirect excitons. So imagine that you have a semiconductor, and you can have a direct band gap and an indirect band gap. So if you have excitonic effects, you can think that the indirect excitons is analogous to the indirect band gap, and the direct exciton analogous to the direct band gap. But what is the idea? We get this and do these calculations for the carbon allotropes. And what we see? First, you have the band gap here, okay? That is the fundamental band gap of the 12 stable semiconductor carbon allotropes, okay? And we have a band gap from 0.7 electron volts until 3.24 electron volts. So it's a huge change, despite all systems have only carbon atoms. And what is interesting, when we see this is the direct band gap, this is the excitonic ground state, and this is what we call exciton binding energy. And we can define the exciton binding energy to understand how strong is this excitonic effect as the difference of fundamental band gap and exciton ground state. That could be direct or indirect. And those difference goes from 83 millielectron volts until to 500 millielectron volts. So you see that it's a huge difference, okay? So for some carbon allotropes, those effects are negligible. For others, are really significant. So for 2D materials, is also important to take care about these effects, to have a more precise estimation. After this, we can calculate the absorption coefficient or the optical linear response of those systems, okay? And we get this at what we call Beth-Salpeter approximation, is the solid curves, and independent particle approximations, where excitonic effects are not taken account, okay? And using the dashed curves. These blue and red curves are from the light polarization, okay, in X and Y direction. And what we can see that's interesting, if we see the last slide, okay, we have the exciton binding energy here, okay? And basically the result of this exciton binding energy can be seen here. If you remember, this one is 8.3 millielectron volts, so it's very difficult to see. But can see other systems that this difference is huge. Look this. Without excitons and with excitons. So excitonic effects are significant for the description of optical properties, okay? And this is very important to estimate the solar harvesting efficiency. Other point that's interesting, some systems, if you see, are not isotropic from light polarization. So the optical response are different, depends of the light polarization. So we can use this property for another application, but it's not the focus of this work. And other question, why I do Beth-Salpeter equation and independent particle approximation and show both, as I'm telling from the beginning of my presentation that excitonic effects are important and I need to consider it. The point is, this is very sensitive. So we can go from this regime to this regime depending on the substrate that you can put below our 2D material. And this is very common from the experimental point of view. Imagine that it's very, very challenging to synthesize a 2D material that is thin as one atom of, thin as one atom. So normally we can do the growth of this 2D material above one substrate. And these substrate effects can be so larger that can kill the excitonic effects. So when we see both cases, I'm showing that, okay, my optical response comes from here to here, depends of which kind of substrate I can put below my material. But okay, using those results, I can estimate the power conversion efficiency. That is basically how much energy I can convert from the solar power. I use a formalism called SLME, that is spectroscopy limited maximum efficiency. What's the main idea? We have the efficiency as the solar power and the power generated from the solar cell. And you can see how much we receive power and how much we generate from in the device. And here we have some expressions, okay? Oh, sorry. But what's important here, that I need to know the solar radiation spectrum. So basically, the sun emits light in this wavelength here. That is basically from 0.5 to 4 electron volts. So if you see the band gaps of our systems, all of them are inside this region. Some materials are more inside there, and other ones more outside there, but all of them is in the region of solar radiation spectrum. When we use this data, this AM1, basically to solve this integral here. So this PE is exactly this curve here. We can use the yellow curve or the red curve, okay? Depends on the approximation that we are considering. In my code, I implement both of them. You can choose. And basically, another thing that's important is this absorbance. And this absorbance is directly related with the absorption coefficients that I show in this previous in this previous slide. So basically, when we do this, we can estimate the efficiency of our devices. But what's important here, I have basically 6 results for the efficiency. And so you can do one question, okay, which one is true? So first things first. First, we can see the Shockley-Kayser limit, okay, is a theoretical limit that only considers the optical band gap and doesn't consider any one of these. Basically, it treats the absorption coefficient as a Heaviside function. So basically, all photons with energy higher or equals than the band gap are absorbed. This is not true. That's the problem. The other one is the SL-LME approximation. So what we can see, we can have some device with 24%, but I'm showing you that using my approximation, we have only 0.45%. And you can ask me, why? You are telling me that, okay, you have approximation with 24%, 22%, but this is very small. What happens? Remember that we have 2D materials. Those things are very thin. So one material like this, it absorbs only 5 or less than 5% of the incident light. So it's difficult to expect this in. If you only put this in the device, it will produce a efficiency around 24%, 22%. It's not feasible. What happens is, if you put it directly the material, unfortunately, we have those small values here. That is lower than 1% of efficiency. But the cause is not lost. That's the point. We can use some kind of lighting trap techniques. We can put a mirror below. We can try to get some insulator and do some sandwich between insulator, monolayer, insulator. Try to make the material more less thin. So, but increase the thickness of the material, okay? And when I increase the thickness, more light is trapped in the material, and we can force the material to absorb more light. And when we do this, we can reach values close to the Shockley-Kayser limit. That's the maximum theoretical limit, okay? This you can use some light trap techniques, or as I can say, you can put several monolayers, one above another, okay? Imagine that the interaction between one monolayer and another is weaker, is a van der Waals interaction. We would have some difference, of course, but it's not expect a huge difference in the in the electronic properties in the absorption spectrum. So we can achieve a good efficiency here, around, for example, for this material, Liskini, 19% until 17%. Of course, this one is without excitonic effects, this one is with excitonic effects. The point of put both calculations here, as I told before, excitonic effects are very sensitive, so imagine that I put this material inside the solar device. It's not only one material, they have the electrodes, you have a electron transport layer, hole transport layer. So we have some kind of discontinuity in the electric environment, and it will change the excitonic response. So that's why what I can show you is, look, if I use those material, and I can trap in good part of the incident photons, okay, I have an efficiency around this and this limits here. Okay? It's important to understand, this is a kind of maximum achievable efficiency. So what I can say to you is, okay, higher than this, forget, you won't get this. Lower, it can happen and probably will happen. Meant that to achieve the maximum efficiency of a material, it can take years. If you can imagine that the perovskites. Perovskites today are the material that, it's a promising material for solar harvesting devices. It has a 25% of efficiency. Okay, if you do this calculation, we can achieve for the same perovskite that people study around 29%. But if you see the first researches in perovskites in 2010, they reached 3%. Now, almost 20 years after, we have 25%. So it takes years of research to achieve this. So basically, when we look at these results, what I can see as a promising material for solar harvesting devices here. We can see this OCD graphene here, this skin here, okay? You can see this OPH graphene. This is another one, almost close to 20%. Imagine that the maximum theoretical limit for a single photo absorber is 30%. So it's very close here, okay? So we can have some materials here that if we do the research, insist, try to produce them, maybe we can achieve the use of 2D carbon allotropes for solar harvesting devices. So basically, answer the first question in the beginning of the lecture. Yes, we can. We can use those materials, but it's a challenge. That's important to understand. It's challenging. You need to understand how to synthesize this. We have no idea yet. We need to see if this is feasible. You can produce it at a large scale, okay? And we can also understand that it can also take years to achieve the maximum potential of these materials. So what I can show you, maybe in 15 years, 50 years, we can see this in your house or in some application. But basically, we can do this simulation. We are looking for the future, not for the past, or not for the present. Okay? So before I finish my presentation, I would like to introduce my research team that do the research with me, okay? So this is Professor Luis from our university. This is Professor Mateus from University of São Carlos, okay? This is Professor Diego Guedes from James Institute of Federal University of Paraná. This is Dr. Carlos Maciel from Fat Cat Brewery. This guy produces beer, but he's a doctor, has a PhD in theoretical physics. Professor Maurício Piotrowski here from University Federal of Pelotas, okay? And Dr. Celso from KIT Institute in Germany. So thanks, and if you have any questions, please we can do now.
So questions, we have time for a few questions.
You mentioned the dependence on the polarization of light in the absorption coefficient. So how does it enter in the Hamiltonian, and why does the absorption depends on the polarization of light?
Okay, that's a good question. What happens is, when I do the calculation, I sum the two polarizations. I meant that I didn't do some polarizator in the solar cell, and I use both. But of course, you can use some kind of polarization filter or something like this and choose one of them. And it can change the results of efficiency. In those materials, what I see that basically the optical band gap doesn't change. The only thing that changes is the intensity. But for some system, for example, is phosphorine, black phosphorus, the optical band gap is different from X or Y light polarization. So yes, it can change the power conversion efficiency. But in this case, for those materials, I sum both of them, okay? It's a way to estimate this. Because the optical band gap really doesn't change. What changes the intensity, but to achievable those 13%, 15%, I consider the approximation that all photon is absorbed. So I can put some kind of mirror or put more layers in the solar absorber. And when I do this, we expect that this intensity will be enhanced, independent of the light polarization. And this doesn't enter in the Hamiltonian, but enter in the light and matter interaction part, not in the Hamiltonian of the electronic part. So when I estimate the oscillator force of the optical transition, we consider the light polarization.
We have time for one last question.
Well, thank you, Alexandre, for your presentation. We have seen that in your process of calculation, you have a lot of phases with different methods being applied, computational methods being applied. For each one of these phases, you have some approach to guarantee that there are not bring error propagation. For instance, when you calculate the densities from density functional and you use these in another the sequence of the methods, can you guarantee that there are not being error propagation in your calculations?
Okay, what happens basically is the following. We start with the FT. The FT is first principle, so we have some error propagation, but it's very small. And of course, when you change one method from another, this could be a problem, of course. What we do that when we use density function tight bind theory, we do a parametrization using first principle results. So the density function tight binding Hamiltonian was parameterized first from some previous DFT calculation. So it will assure that this propagation error would be lower. Of course, it's not zero, okay, we have some problems. But for carbon, density function tight bind theory works well. For other materials, doesn't guarantee this. So I avoid to use this method for other systems, but for carbon, it really works well. So we do some tests during the work. We get some, okay, this is the FT, this is the FTB. The results are quite similar. We see some error in the structure properties around the 10-4, which is reasonable, okay? And when we go to tight binding methods, we doesn't use the FTB as a start point, we use the FT. So when I do the maximally localized linear functions tight binding Hamiltonian, basically the tight binding Hamiltonian model is fitted in the FT calculation, not the FTB. And what you can show in the work is that the Hamiltonian for the description of the lowest electronic levels, close to firm level, the description is very accurate. For the other levels, so I don't know, if I want to see a level 10 electron volts above the firm level, this doesn't guarantee, but I only see for absorption spectrum the first levels. Basically, it's the levels that experimental have access to do the measure. So we work with the tools that we have. But what I can assure is that we try to do the best to get something reasonable and reliable.
So I think we have to move on to the next talk. I'm told that there are some questions from YouTube transmission. So you're welcome to reach out to Professor Alexandre Cavalheiros later on by email, because right now I think we don't have much more time. Okay, so thank you again. And next stop. Next speaker is Professor Lauro Tomil from IFT, Unesp, who's presently also visiting professor at the Physics Institute at UNB. So please welcome to the stage.
Okay, thank you very much for the presentation. Hello, hello.
Isso desse jeito aqui. Aí fica em cima da... Isso, aí vamos falar.
Alô? Alô? Tá ok?
Aí deixa daqui no bolso, pronto.
Okay, so thank you very much for the invitation. As he told me, I'm just here in the University of Brazil, a visitor for a while here, for 1 year at least. Let me see if this is working here. Sorry. This is a pointer also? Okay. Okay. So this is the title of my presentation. Is working about stability and Faraday waves on bubbles trapped boside condensation mixture. Okay. So this is in a collaboration that I've done this last year, and also we are trying to continue something related with Leonardo Brito, Alex Andreatti, and Arnaldo Gamal. Arnaldo Gamal was the supervisor of the other two guys. So first, my outline here, I present first some introduction about bubbles in cold atoms, the stability of atom mixtures in a bubble, and solution with azimuthal symmetry, and linear perturbation when azimuthal is S0 or S1 equal minus S2 equal 1. And second part is more about Bogoliubov-Digenis stability analysis, mixture in periodic regimes with Zeeman field, and Rabi coupling, Floquet analysis, and after give my some conclusions. So why this motivation? Bubbles in boside condensation is explored in different geometries first, and treatment of a system with real 2D periodic boundary conditions. That's much easier in some cases to treat numerically. And long-standing possibility is the shell geometry of trapped atoms, trapped system. Bubble trap inaccessible on Earth due to gravity. So these also are experiments that are being done also by the NASA Cold Atom Laboratory at ISS. One of the first papers about this is about this Zubai at the, and Garaway here in 2001. And after is also a very good paper here about microgravity works here in 2019 about what is being done. And there is also recent work on bubble and with bubbles. There are several works here being done also in Brazil and the other place here. Okay? And some reviews also done by the group of San Carlos. Okay, so the back experiment in space is more described here also by these papers in Nature here, and also by Abelin here, and this shows also some pictures of these cold atoms. That one could think also this is still under investigation because the complete, I think, condensate is not well done till now, well observed till now, but only that very close to that. About exploring mixture in bubble geometry, there is a first also paper here by this group here, and in 2019 about ring geometry. Not exactly a bubble, but at least the ring geometry is more close to that. And these are the paper by Zubai and Garaway, and show how to realize this. And this is the kind of a bubble potential, where if you go for very large delta here, you can go from this situation to this situation here, that in one dimension looks a ring, but can be a bubble also. So the condensate in spherical shell, that's the main calculation here. The radial can be solved analytically also, that you can end up with this equation here only with kind of kinetic energy and this about the interactions once done the radial part. Of course, we are talking about just a skin of the radial in that case. So this is dimensionless model, becomes like this for one atom trapped, one condensate, and these are the units to remain in the dimensionless model. So this stability of back mixture is our main that we have investigated, and the dynamic behavior of a back mixture trapped on the surface of this rigid spherical shell within the mean field level, exploring the miscibility of the interaction by considering repulsive and attractive interaction. To compute the critical stable points, we follow the Bogoliubov-Digenis method for the analysis of perturbed solution, with the constraint that initially the stationary states are in a complete miscible configuration. Beyond this small perturbation, we also explore the dynamics with full numerical time-dependent formalism. So here is basically the model that we are describing here. Some of my transparency are more detailed things that people can go through after my presentation here. So you assume the two species with the same mass, in this in a homogeneous mix, with both species have the same density. Equal mass are supported in Bose-Einstein condensation experiment with two spin-offs of the state of the same isotope. The stability will be studied by adding small time-dependent perturbation. We are concerned with dynamic stability because energetic stability are not being considered as we are taking all the theory in terms of T equals 0, temperature 0. So energetic stability plays a role only in the excited states. So this can be studied in this by Pitaevsky, Stringari, also in Bose-Einstein condensation, superfluidity. So these are one of our main parameters is the two atoms scattering length. The inter and intra-species interaction, we describe this as intra-species when I equal J for the same condensate. And when are different here is that interspecies. So when this ratio here is large increase, unstable mode should appear analogous to the one-dimensional ring case that was studied before in this paper here. So we take the two species confined in the scheme of the spherical shell with the radius r, when the condensate be only inside an infinitesimal range like this trapped region as this volume here. And so effectively, our wave function have a delta Dirac here. We can describe it this way, or by some representation with this delta Dirac, and this is the wave function that depends on the angle, the angular position, and the time. So to validate the assumption here, there is some study by Beret et al. In the American Journal of Physics that shows what conditions that this can be realized. So the energy absolute obtained from the nonlinear quartic interaction for each species, the ground state here, and for this smaller than this provides a strict range of validity of our reduction from 3D to 2D sphere, which can be controlled by these two parameters, the number of atoms and the two-body scattering length. So this two-body scattering length in dimensionless unit, we can write in this way here, by this gamma parameter. Sometimes I'm also using the G parameter that was when we have dimensions. So N is the total number of atoms, the summation. So that's the model formalism. So it's, as you see, it's a quite simple structure that one can follow also from quantum mechanics basic. So these are the angular momentum operator, basically. And here is the interaction, the one species, the second species, and the interspecies interaction. So this is the proportional to the square of the angular momentum, and this interaction, and this is the coordinates here. So the wave function normalized to the number of atoms in this way. So each component is normalized to N1 and N2, with the corresponding functional energy given by this term here, where L is the operator, the moment operator. So with the initial non-perturbed stationary solution normalized to 1, we have this equation here with this mean the chemical potential with dependence assumed with charges as this charge was integer number defined as initial vorticity for the components, which gives by LZ as a as here's the integration here. So the vortices are created on the sphere for SE not zero. So SE not zero affects this function here, boundary condition, due to the terms that we have in the Laplacian here, implying that this condition, f pi should be 0 for this different 0. So the stationary solution of the linear part are, when you take this equals 0, so you have only kinetic energy there, are the well-known spherical harmonics in which the associated Legendre function are this one here, are the solution for the theta variable. So with this different 0, we can generate a multiplicity of stationary solutions for a coupled system emerged from the linear one. So this is a linear perturbation that we introduce here. That is the term that is given the perturbation, time dependent, and the expansion in azimuthal modes described in that way here. Okay. That's the following the simplest solution and learn about their stability, as well as the vorticity when considering opposite values of the azimuthal quantum number Sj. We start by considering the non-vorticity case when this is equal 0, just as an exercise now. So that's the first case is just a constant here, and here I'm just discussing the possible nonlinear stationary solution can be split into two distinct cases now, related to miscibility, following a simple energetic consideration, as explained in this paper here, comparing the nonlinear energies contribution to a complete miscible with a complete immiscible one, with the two species are not interact, but constrained with the same total volume. One can show that immiscible configuration, in this case here, provides the lower energy. So as this is not an exact relation, a more detailed stability analysis is required, in which the trap geometry and kinetic energy term can also be relevant. So these are some details that how we take the perturbation as expanded in terms of spherical harmonic for convenience, of course. The oscillating modes are assumed in general in complex quantities. Okay, that's the modes of oscillation for all values of L implying stable solution. Okay, in that case, you can study the possibility for instability when this part is non-zero, and this when it's zero is a stable solution. So by solving that equation that we have original, we got this the general expression depending on that the angular momentum from operator and this the interaction that interspecies here and interspecies. Of course, this we can go to negative or positive of all these interactions just to study the possibility. So as a general outcome, you know that the solution becomes unstable for overall attractive interaction because this becomes negative, and in that case, this becomes complex, you know, with the imaginary term not non-zero. So we are going to assume, for example, gamma 1, 2 equal gamma 2, 1, because this is the same when the numbers of atoms are identical. And considering so G1, 2 is equal G2, 2, 1 for both particles. So this is what we can get if in case that you have gamma 1, 1 equal gamma 2, 2. Is the intra-species are identical. The stable region is this one for L equal 1, and these are unstable. And the same for the L equal 2, and L equal 3 is the same rule here. And the other case, as we have checked here, is when we have inverse. One is attractive, and the other is repulsive. In this case, the stability only can be realized inside the circle, for L equal 1, L equal 2, and so on. So these are simple possibilities to occur. The oscillating modes become independent of the signal of both gamma 1, 1 and gamma 1, 2, because this is expression. With stability frontiers for each perturbation being circles. That's the radius. Okay. So this is imaginary modes for this case here, when the interspecies equal 10 as function of gamma 1, 2. In that case, we can study where it appears the instability for each L. But of course, by examining overall here, what we can see is not each one separated, but this is the result that we see. Following, for example, the first case here is the black one here. So we can study the stability or how they become unstable by going to different parameters, gamma 1, 2, taking that gamma 1, 1 is equal 10. But we can also change these parameters here and just check the other region. And this is how the wave function goes in case that they are completely miscible. That is the case here, where gamma 1, 2 is equal to gamma 1, 1. And this, when gamma 1, 2 is large. When it's large, it becomes more unstable. Okay. And when it's very large, you see that it becomes completely for the two species. Né? It means that it becomes immiscible. Né? So they are separated. The overlap. Okay. This shows that the system goes from miscible to immiscible case. So we assume both species initially with the same density in the lowest non-interacting stationary state and oppositional vortices between the components. In this case, we are taking non-zero Sj, no? But in opposite signal. So the states are initially in a completely miscible configuration and hidden vortices. By hidden, we mean here that no net angular azimuthal momentum, despite each species have a single vortex, no? Single charged vortex. This implies that this must vanish at the poles to avoid divergence in the kinetic energy, as I also mentioned before. So that's the solution for the chemical potential. And this is the eigenvalues. And these are the equations that are developed here. Né? For general solution for the non-perturbable stationary equation with different possible gammas, we found appropriate to apply numerical techniques, particularly by taking into account the stability analysis, which is done with time-dependent small perturbation. So the numerical solutions are obtained by starting with analytical continuation from the non-integral interacting case to arbitrary interaction dimension. As you see from the simplicity of this, we can also treat this variational. For variational, we treat in this way, taking this as a variational function with lambda and beta being the variational parameters. So these are the solutions in that case that we have, just comparing this solution, where variation with the numericals, just to see how it goes also with different parameters gamma, where gamma here is the summation of gamma 1, plus gamma 1, 2. Okay? Just to see how it was working, the variational procedure. Only the best quantities to examine how variational is working is the function f here, the wave function. So by the general stability analysis, we take now this wave function that expand in this infinite time-dependent perturbation, where each one is given in terms of this wave function here, or m phi, where m is the mode that we are considering. That is the integral number, factorating the azimuthal symmetry. In that case, we can insert in the solution, we got the matrix, the Genus matrix. With this term, this is the eigen solution. The imaginary eigenvalues of M return the unstable mode, okay, by solving this equation. So these are the solutions in this case. S1 equal S2 minus S2 equal 1. Okay. This is my respect for M solution. For different M solutions, we have the solutions here. These are the stable part, and these are unstable, considering this case here, as exemplified by gamma y 1 equal gamma 2 equal 10. And that's in case of the with 0 here, and we are seeing how it goes with gamma 1 equal gamma 2 here, the stability for different values of M. These are the complete full stability diagram that we have. Okay? That we draw, and after we can study also how it goes this numerically. You can also recheck here. And here you can see, for example, the complete miscible configuration, and after here, unstable. You can see one gamma 1, 2 equal 8, and the other gamma 1, 2 equal 12, that become unstable. Okay. These are the stable case that becomes mixed with all the time, and these are becoming mixed with this time. This is the overlap parameter called the immiscibility parameter, or overlap, the wave function 1 and 2. In that case, from this equation that we can measure, and we can see that this kind of behavior, if you go for large times, you can see that's a periodic oscillation here that becomes stable, and after again and again, and so on. Okay? And these are the study about density plots for n equal or for example, instability. When this is equal 10, and that's the 95, because we choose from the general diagram of this values here now. So when this is dominant, this case here, we can see this part. If they start the two species, one species and the second species here at t equals 0, identical, completely miscible. And here, they, with the time growing here, become unstable, and the final situation here in the top, here is a look from the Y here with Z, and that is the other way for this, the first species, and that's for the second species. You can see that it becomes completely separable here, because you can see the position of one species here, and that's in this way here. So they becomes immiscible. They start with mixed configuration and end up in completely immiscible at 4.15 times. That's for M equal 3. In that case, we have to choose in the general diagram a situation of parameters where this can happen with this equal 10 and this term 1, 2 equal minus 3 for 34, the interspecies. In that case, this is the densities I'll start, and also, of course, here is 1, it's not shown here from t equals 0 to t equals 7. But after it becomes unstable completely, and also it goes to this situation here. There is 3 maximum in this case that the phase can show better. 1 is hidden behind here. Okay. So the density for a complete mixed configuration is lambda equal 1 is shown here. Okay. 3 instants close to the collapse dominated by m equal 3. The maximum are in the 3 position of phi. And we find the lower row where the density have a radial representation with the phase map of chord. In this case here, we have the 2 species LZ with S1 equal minus S2 equal 1 before the collapse and after what happened in the collapse. So that's conclusion about this homogeneous mixture in a bubble. Homogeneous, it shows that it can turn unstable depending on the inter and inter-species interaction. In bubble confined geometry, critical point stability is extended as in ring, and unstable mode can be analyzed by the BDG method with the time evolution confirmed. Now I'm just passing to the other part here of mixed within periodic regime, where we can find these Faraday waves on a bubble. For the dynamic stability of condensed mixture trapped on the surface, it was considered Rabi coupling in that case from between the species, which can modulate interaction, leading to parametric resonance. In this case, we can verify the possibility to induce and or avoid instability in a bubble with different coupled states. So the discrete angular modes drive both phase separation and spatial pattern with Faraday waves emerging and coexisting with an immiscible phase. As shown in this discrete case, the only parameter that we are using here to drive the emergence of Faraday waves are the S-wave contact interaction and the Rabi coupling. Once analytic solution for population dynamics are obtained, before make this analysis, stability analysis, the stability of homogeneous mix is investigated via Bogoliubov-Degenes and also by Floquet method, with prediction being analyzed by full numerical solution. So Faraday waves, for those who don't remember, they are known as the spatial patterns being observed in different branches of physics. Whenever describing nonlinear wave propagation, as in fluids outside equilibrium and nonlinear optics. Surface wave excitation were first noticed by Faraday in 1831, following a famous experiment. The formation of patterns is shown in vibrating surface. So how Faraday waves can be achieved in closed geometry, especially when the excitation is led by Rabi coupling, was the open question that we have considered. So our focus was homogeneous condensate coupled by Rabi oscillation. So that's the main equation that we have. And that we are based also in some other work that was done also before by Chen, but not in a bubble. That's in a plane surface here. Now we are trying to see what happens in a bubble here, just extending this kind of work done by this Chen et al. Here. This is the Rabi coupling here, the 2 species. And these are the equations that we have before, the same as in the first part. So with the 2D coupled wave function normalized to Nj, in a simple case, where G equals G1, 2, the coupled wave function can be solved analytically given this format here. The period of oscillation, which does not depend on the interaction, being twice the period for the densities, the pi divided by omega. And for this non-zero, a more general periodic solution can be derived. That we have derived this format here, more general in our work there. No? In that case, for the difference of zero here and for omega non-zero also. No? And where the densities are taking this as a periodic complex function for the period T. There also we have discussed in the paper the case that we treat this as a complex also quantity directly here. So with both states equally populated, T equals 0, we have the same condition here, a constant here. But the atom number is given by this, oscillate within a cycle given by the T and the amplitude A. A is the maximum number of radiation particles. So with delta G equal non-zero here and omega non-zero, a general solution can be obtained with time-dependent phase, not identical for both species. For the stability analysis, we can consider they are carrying only the identical constant part here, such that the time dependence of the phase are provided by the function Fj here. That equation is satisfied by this equation here. No? These are the densities for the second component, and this is the first component here. And this delta G is the difference of the G12 minus G, which is this is the difference of the scattering length corresponding for the interspecies, it is intraspecies. Of course, here you have put only G because we are considering G11 equals G22 here. Okay? They are the same for the intraspecies. For the atom ratio difference defined by this form here is given by this term here, can also put in another similar equation there, and we can see that this satisfies the undamped, unforced Duffing oscillator. There is a long study about this Duffing oscillator here in more general case, but in our case here it's undamped, unforced. So it is very simple and very similar to the harmonic oscillator formalist here. So the Jacobi elliptic periodic functions are the solution having this period when alpha is the amplitude and delta G divided by 8 pi here. So this, as you see, if this was a constant, not a time dependent, should be a simple, well-known solution already. So considering the resemblance with the harmonic oscillator sinusoidal formula, we could also put this solution there and consider this as parameter that we can adjust considering the exact solution, and also variational we could get also this easily. Okay. So these are the dependence of this amplitude in terms of this, and this is the period that is given by that here. This is taking this ansatz here. But of course, this should be compared with this period here that's exactly given by the Duffing oscillator. And this is the comparison of this result that we have for the period. For the period T is given by a function of delta G here, and with this alpha, the Duffing period Tk, empty triangle, is in perfect agreement with this T obtained for that ansatz there. This is solution here. So this is for how we change here the number, the time evolution of the atom number ratio. How they change according to this in different situations. When delta G equals 0, this is very simple and analytical. And this is the case when delta G is non-zero and now independence with omega, with the Rabi coupling. As you see, as the Rabi coupling is decreasing here, you can have this situation going from this situation here, 0.2, to this situation that becomes very long here, one period. So the time evolution of this with the initial condition n0, n by 2, the total n with the Rabi coupling. So these are the densities, the solution, when this goes to 0, where omega is much smaller than this. Both densities have this case of stationary case. As delta G increases, the atom exchange period decrease will reach in the stationary limit, as I showed before in the previous transparency. With respect to Rabi, more time is needed for the unoscillate solution to complete each cycle in that case, with lower values of omega than the higher one. This now we are treating the Rabi coupling on the role of the Rabi coupling on the stationary solution via BDG method, Moguliv-Degenes method, and with this expansion here. Okay? And these are the corresponding matrix equation. I'm not showing explicitly here the matrix, but that's the equation that we have to solve with this four components of this vector here. No? By solving this corresponding determinant, 4 possible solutions are obtained. These are the 4 solutions. Of course, only 2 solutions are relevant here, considering the 2 are identical, just change the signal. The system is always taking dynamically stable if these frequencies are real, and dynamically unstable when they are complex. These are the complete diagram of what is obtained by BDG method in that way. That is the stable region here. That is the level of that we have instability, but is stable maybe only in some region here as we decrease, you increase from 0.1 to 0.9, you can increase a bit more this part here, okay? These are with growth with G negative. G is the intra-species, and this is interspecies interaction. So to better take into account the role of Rabi coupling in the dynamics, we can study the solution dynamically by the time-dependent Floquet method with small oscillation. We consider the phases here having a common time-independent part and with Fj being complex. So now we take again here this expansion with this time-dependent here also with this gamma, and where the amplitudes here are periodic time-dependent function with the same period t as Fj, such that this we have this condition here. So this is the complete matrix for this analysis with the Floquet method, where these are for the 2 cases here that we have, and here is the equation that finally we have to solve numerically that thing. So according to the Floquet theorem, exist solutions that satisfy this, where lambda is a Floquet exponent. Is given by this form here. The eigenvalues and eigenvectors correspond to this term here and P0 here. So the Floquet theorem is this one here. The evolution a complete period t gives this. So we have to find if real t is 0, real the home here, or if there is some imaginary part of the instability. That this is the spectrum that we obtain for the maximum. For the maximum of maximum real here, okay? That is the region unstable in that case. That for when they are real in that. So that's the maximum, and here you can see the instability, and here are the stable region. These are just a zoom that we take for some very small point here that appears in some place here, okay? And these are the same that we take from different parameters here, just studying the stability. That is the diagram. As you see, we are treating the same problem, but now the diagram is slightly different from that one that we have before here. No? That is the stable region here. That with the 1 here and 2. And that is with all L equal 3 here, 1, 2, and 3 here. That is the unstable level that we have here. No? And that is how J goes from attractive to repulsive interaction. This is also attractive to repulsive interaction, G12. This is the L equal 1 dominant dynamics. With G equal 1, G12 equal 8, and omega 0.5. The parameters, these are the population are exchanging, and you can see only some instability occurring only for very large times here, okay? So dot is a homogeneous solid for full Gross-Pitaeva solution numerically. And these are the parameters we are using, and this is for one component and second component at t equals 0, completely miscible, and after become immiscible for some point here at t equals 58. No? And these are for L equal 1 and 2 dominant dynamics. In that case, we can see also for these parameters here, the L equal 1, and for L equal 2, second case here, that equals 0, and D to D is L equal 2. And this how it goes, the dynamics of population. 0.9 is G equal minus 10, G12 equal 20. So the dynamic of population and immiscibility together here in blue. These are the case of L equal 1, dominant periodic instability occurring. And these are the components developed this instability after a long time here, okay? For this parameter here. This complete here, you can see some instability here, but after returning here, so it's something periodic. These in blue here are the miscibility curves. We start on 1, and if complete stable should be just a line here. Okay? And these are the case L equal 2, when L equal 2 dominant. It's a destructive instability. In that case, start in this way here, and after you can see also this blue going in this way here. The overlap, no? That miscibility, let me say. And these are the population dynamics. And after here, you can see it is broken, this population dynamics. And this is how we can study also numerically, how it goes with different M components, just introducing numerically, just to see the instability, how it occurs in the calculation. This is the time of first set of overlap parameters for that we choose some coupling there. For lambda 1 is 0.5, 1, and 8. And this is the case here, where we have this instability very clear here occurring. Looks periodic also, this thing that appears. And the other case is this one, with lambda equal 2, with this parameter here. These are G and G12. Lambda 3 and lambda 4, as you can see, for this parameter are completely stable. It becomes 1 for any times there. No? So are identical solid in violet and solid in red. So lambda 3 is shown in the inset here just because of that, because they are just to show how far we went, just to see if there is some numerical instability or not. Okay. So the conclusion. The dynamics and stability of homogeneous back mixture on a bubble are investigated by using Rabi coupling, atom number oscillation. Exact solutions are followed by stability analysis using the BDG and Floquet method with full numerical solution. The role of Rabi coupling on stationary solution is studied by BDG method. The time-dependent Floquet method was shown more reliable, was appropriate for a detailed analysis of the dynamics. The Rabi oscillations are able to drive the system to different stability profiles. Once an effective time oscillating interaction energy is performed. So discrete and stable orbital angular momentum can rise and lead the Bose-Einstein condensation mixture to an immiscible phase separation in which the condensate can break into discrete numbers of localized clouds. The unstable generate azimuthal angular modes can give rise to the Faraday waves for some range of parameters. So the system can enter a periodic regime where the immiscibility of the space varying dynamically in time. So these are the perspectives that we have for future here. Just advancing some possible questions here. More general 3D study is one of the directions that we can examine active topology, taking, for example, instead of just a scheme, take some radial also condition there. Okay. Some different radial function. As only discrete modes are allowed, a phase separation where the coupled condensate breaks into localized fixed number of clouds presents a density order much higher than the Faraday wave patterns. So this should be studied so the Faraday wave phenomenon can be hidden within this process. So this one should be examined in more details because this Faraday wave phenomenon can be hidden because of this problem. So the stability of dipolar also coupled system on how nonlinear quantum fluctuations could affect the outcome of. That's another possibility. So these are, for those more interested, are the main two papers that I mentioned here. And for partial support, I have to thank my agents. So thank you very much for the attention.
We're encouraged to approach Lauro and all the previous speakers during the poster session, which is also coffee break with complimentary drinks. So please, let's thank Professor Lauro Tomio again. Alô.
Так, а где эта штучка?
Alô. So the last speaker of today's oral sessions is Professor Victor Dodonov from the Physics Institute at the University of Brasilia.
Okay,
Thank you.
thank you. Okay, this is title of my talk. It is based on recent papers prepared and published by me together with Alexander. And when I worked on the slides, it is April, and I remember that April 22 is the birthday of Vladimir Lenin, one of creators of Soviet Union. And during great part of my life, I remember that we always celebrated this date until the last days of Soviet Union. And I remember that in many papers and books, people put on the front page some, not summary, some very short preface with words of great scientists or great people. And so I remembered famous phrase which every Russian scientist knew from the heart, that an electron is as inexhaustible as an atom. It was written in the book by Lenin, published in 1909, named Materialism and Empirical Criticism. Book is not very easy to read, but we were obliged to read it, and I read, and it was not bad. And why he wrote this phrase? Because at the beginning of 20th century, you remember that many great physicists believed that physics was already finished. Only some small details must be added, but there is no sense to continue to study it. It is over. But Lenin wrote that
this is not so, that a lot of things waits for us in front of you. So let us see why I remember that phrase. Because I shall tell about two systems, some generalized harmonic oscillator in one dimension, and two-dimensional system, a particle magnetic field, which is reduced in some sense to this problem. And you may ask, why to study this very simple system? It is textbook system. Any child knows about this. Yes, any child knows, but in the case when the parameters are time independent, and when they depend on time, it appears that until now some things were not discovered. And I shall try to convince you in this. So, what we know? We know that quantum mechanics of oscillator is very similar to classical mechanics of oscillator. At least practically all solutions of quantum problem can be expressed in terms of solutions of the classical equation of motion. This was shown in great details at the end of 90s, one of famous papers by Lewis and Riesenfeld, and another paper by my teachers Ilya Malkin and Vladimir Manько, and Dmitry Trifonov, who was the PhD student in that time. And some stimul to my study was a series of papers with my PhD student Mateusz Horowitz, when we studied that systems with some concrete time dependencies, because some general solutions in general form were obtained already in that papers, but concrete systems were not studied. And when we studied, for instance, with this time dependence, why we chose this, because it can be solved analytically, and I like analytical solutions. What was discovered? We calculated some things, especially mean energy and magnetic moment, and what appeared? That we considered different regimes. You see this time dependence, and parameter kappa is responsible for the speed of evolution. If kappa is very big, evolution is rapid, practically instantaneous. But if kappa is very small, this is adiabatic evolution. And what we discovered, what surprised me a lot, but when we begin from some initial frequency, positive frequency, and we go to some final frequency, if this final frequency is positive, you see this straight line. It is well known adiabatic invariant that energy proportional to the frequency. But if the energy frequency becomes negative, we see here, for instance, that we almost have straight line, but another inclination. And what was surprising, you see inclination, for instance, here, 1. And here you see 3. So when we change the sign of frequency, energy increases 3 times. And we tested different time dependencies, for instance, another time dependence. And here that straight lines were seen with much more precision. And it was a question, why this happens? Why energy increased 3 times when we change the sign of magnetic field? And remember that there are well-known adiabatic invariants for harmonic oscillator, that ratio of energy to frequency is constant when frequency changes very, very slowly. Okay, and let us see how this happens, because then we have solution when if frequency is constant, then we see, remember, exponential of omega multiplied by time. If frequency changes slowly, it is almost obvious, this is famous quasi-classical approximation. Okay, replace product omega by time by integral. And the next approximation will give us this prefect before exponential. But when this can be done, if we put the solution to the equation, we shall see this thing, and we see that adiabatic regime happens when we can neglect these things, and there are these conditions. And we see that when frequency is very small, goes to zero, obviously adiabatic approximation cannot be used. And what to do in this case? What to do if the frequency passes through zero? The first answer is forget about this question, no do. But there is another answer, and as a Russian scientist, I like Russian literature, and there were famous writers, Arkady and Boris Strugatsky, and one of their books was named Monday Begins on Saturday, a book about some research institute of magics, or maybe quantum magics, and one of leading magicians, Cristobal Josevich Junta, told that why you try to solve the problem where we know that solution exists. Then it exists there. You should not spend your time on this. The real question is what to do with the problem which has been proven to have no solution. So thinking in this direction, we arrived to some results published in our papers with Alexander some few years ago. And what we did, Alexander did really. First, we decided to look at a classical problem. So we use this equation for harmonic oscillator with time-dependent frequency, and we use initial conditions. For instance, we fix initial energy, and then we have some parameter of phase, because initial coordinate, initial velocity, and some phase. And what will happen with the solution? What we are interested in the evolution of energy. So we can use some dimensionless variables. So we look for this ratio in instant energy to the initial one. And this ratio in general case depends on what? On time, or some dimensionless time, on some adiabaticity parameter. Because this, if tau is time of evolution. If tau is greater, evolution is adiabatic. Tau is smaller, evolution is instantaneous. This parameter G. And the initial phase. So this function of three variables. In adiabatic invariance means that if this parameter G is big enough, then dependence on phase must disappear. We obtain so all functions depend only on time. And what happened when Alexander showed me numerical solutions? Well, let us look at dependence what? Power dependence of time. Some nth power of this dimensionless variable. And let us look, so when this time t is negative, this what happens before frequency reached zero. If t is positive, then we already passed zero. You see, t is minus 1/2. We see some oscillations and strong oscillation dependent on phase. You see this 0.7, here is 1, okay, for different values of parameter n. Now we tell G 1000, this adiabatic regime. And you see, at the first glance, figures are the same. But pay attention to the scale here from 0.7 to 1. And here 0.8404, here 84012. Therefore, oscillations exist, but the amplitude really is very, very small. This means that we really have this adiabatic invariance. Energy practically constant, proportional to frequency. And now let us look what happens if we pass zero. Figures are very similar. You see, G is 1000, it is a adiabatic regime, but dependence on phase did not disappear. We see that dependence. But you see one interesting thing. For instance, n equal 2. strong oscillations, and look at the mean value, 3. N equal 4, look, mean value about 7, okay? And then Alexander calculated the dependence on mean value, okay, of this number n. And it's numerical solution. You see, n equals 2, 3, n equals 4, 7. It was done for different time dependencies. What was common of these time dependencies? Well, you see, time dependence can be arbitrary, but when we reach 0, it is important how we pass 0, reach 0, or linearly, then n equals 2, or quadratically, n equals 4, and so on. So it depends on the behavior near 0. And you see that there are strong oscillations, but there are mean values which are fixed. And now we remember where mean values appear automatically. In quantum mechanics, what we do, we calculate these mean values. And I remember, repeat that problem was solved many years ago. One of fundamental papers by Husim in 1953, and then papers by Popov and Perelomov, Louis Liesenfeld, Malcolm and Contriefan, and some others. But this was done in general form. It was shown that solutions of quantum problem depends on solution of classical problem. But concrete solutions were not considered at that time. I understand why, because concrete solutions need numerical calculations, and great theoreticians did not know at that time how to make these numeric calculations. Okay, now what we see? It appears that it is useful to use complex solution of this equation, and there are two independent solutions with the complex, and we can choose the value of Wronskian, this here. And then this way have mean energy, everything can be calculated in terms of these complex solutions. And if we do this in the adiabatic regime, remember that adiabatic regime is this solution, then immediately we obtain this ratio, that the ratio energy to frequency is constant, provided this adiabatic approximation is valid. So when we did not reach 0. But what happens if we passed 0? And this great idea was the following. If we pass 0, and if we are not very close to 0, then adiabatic solutions appear again. But you know that the equation of the second order, there are solutions with positive phase and with negative phase. Therefore, in this case, we have superposition of these two solutions with constant coefficients, u plus and u minus. And the value of Wronskian, if we calculate, means that there must be this identity, modulus u plus and minus modulus u minus squared must be equal to 1. Okay, then if we use these solutions, what will be the result? We calculate the ratio of energy to the initial one, and we see that this ratio is again proportional to the instant frequency with some constant coefficient. Constant coefficient has two parts. One part does not depend on the initial state. See, is given immediately by sum of this modulus squared of parameters. And the other part depends on the initial state. So to simplify all formulas, we decided to use initial state satisfy these conditions. This is Fock or thermal initial states. Then very simple formula for this mean energy. Okay, and this shows that when we pass 0, energy will always be bigger than initial one. Okay, then what happens? We can consider that same dependence of frequency at the quantum regime to solve this equation. And this equation is reduced to the Bessel equation. And about Bessel function, we know practically everything. So we can calculate this some explicit formulas. We can calculate this ratio. This ratio is given by some complicated expression, but it contains products or squares of Bessel functions of positive and negative indices. Okay, and then using the adiabatic formulas or formulas for large values of arguments, for instance, we obtain the formula. If we did not pass through zero, you see what will be 1 minus cosine squared, and denominator sine squared. It will be 1, okay? But if we pass through zero, then will arise sine plus, and we see this coefficient. And we have exactly this number, 3, 7, and so on. So we know what will happen if frequency of oscillator passes zero adiabatically. And okay, this is the same. This is some details. What happens that slowly, class. Of course, there is no discontinuity, some slow pass, but we see exactly this inclination 1. This is inclination 3 in the case of n equals 2. Okay, and now the question: what will happen if the frequency passes zero many times? This question is related to magnetic field, because what happens in magnetic field? If we have not very strong magnetic field, about 1 Tesla, then we can calculate the frequency of rotation of electron is about 1 gigahertz, 10 to 9 hertz. And now our standard frequency is 50 hertz. So if we have solenoid with alternating current, then this is exactly adiabatic regime, because frequency of oscillations of current is 8 orders of magnitude smaller than the frequency of rotation. So we can ask, what will happen if we pass through zero many times? And you see that if we have initial function with positive phase, then it will transform to the superposition of function with positive phase and negative phase. Then we have passed through zero one more time. So how what happens with this function? We know. What happens with this? Of course, we have to take a complex conjugate solution. So and then if this goes transforms complex conjugate solutions, and we can easily find some recurrence formulas. After n passes through zero, we have these recurrence formulas. But what appears here? Some phase. What is the phase? It is interval frequency between the first passing through zero and the case passing through zero. And you see that we have strong oscillations, because if we slightly change the time between two passes through zero, we have changed the result drastically. For example, if we have only 2 passes through zero, we have this some parameter of amplification. It varies from square of minus 2 things to square of plus 2 things. For instance, the simplest case, when that n was 2, minimum will be 1. Okay, the energy can return to the initial value, but maximum in this case is 17. It can be 17 times bigger, not if we pass through zero once, 3 times, twice 17. And if we do more transitions, it is difficult to prevent. What can happen? I suspect that can be some kind of quasi-stochastic regime can appear. So for classical illustration, what is this typical dependence? This sine squared, okay? Then this phase depends on this great parameter g. And you see, for instance, we take g about 1000, okay? Then variation 2 pi correspond to change of only 5. And you see pictures. This is a figure when we pass through zero only once. Depends on this g. You see figures different. But if we take some mean value, it is 3 for all possibilities. But now if we pass twice, you see, for some values we have strong oscillations, but for other values, practically nothing. You see that in here, everything will vary from 1 to that number about 17 this time. So this is a very interesting result. And we thought about the following thing. We see that, for instance, we take the initial Fock state, suppose first Fock state. We know that after passing through zero, energy changes 3 times. What will be with the state after this? We can think, first Fock state will go to third Fock state, energy will be 3 times bigger. But this is not so, because before showed that great oscillations. Therefore, mean values change 3 times, but there are great oscillations. So great variance will appear. Therefore, we can ask, what is the probability to obtain our function? This is given by this expression that was obtained by Malkin and Co. many years ago. Then we have that probability to go to other states given by associated Legendre polynomials. And we see that if U plus is 1, this is Born-Fock theorem. The state doesn't change. But in other case, we have this probability with different from 1 below. And what will be distribution? A distribution is given here. You see, for instance, initial state is 10. Energy multiplied by 3 times. Mean energy 30. But probability to discover the state with 30 is 0. We have almost 50% probability to discover states with n greater than 30 and almost 50% smaller than 30. And you see, bigger the n, more regular structures appear. So this is a very interesting result. Okay, this is one thing. Another case that we discovered recently, we can look at harmonic oscillator and this function gamma of t. And when this function, not frequency omega, but omega squared change the sign, we can believe, okay, it can be some joke, but a lot of people study this systems. I discovered almost 100 interesting papers, including some papers and results by Roy Glauber, one of creators of quantum optics. And I remember quite well in some conference nearby Moscow in 82, he gave talk where he considered this model. I was very surprised why great people look at these toy models, but it appears that model rather interesting. What will happen in this case? In this case, the solutions, of course, when frequency pass gamma frac 0, Bessel functions will be transformed to modified Bessel functions. And some coefficients contain differences of squares. But you see, time is great, so this parameter zeta is great, and we use asymptotical formula for this modified Bessel function. For usual Bessel functions, sine or cosine, here exponential. And what was a great surprise for me, we are accustomed to that in many cases it is enough to take only leading terms of asymptotic expansion. But if we forgot about this series, take leading terms, they do not depend on the index of Bessel function. This will be 0. Therefore, the first result was that when frequency, then frequency squared become negative, mean energy will be 0. It seemed very nice, but it is not so, because in this case, we have to take into account the next term. We see the difference. When we have usual Bessel functions, corrections are very small, and they are multiplied by cosine or sine. It is nothing. But when corrections small by multiplied by exponential function, they will give great result. And so then we calculated this, and the ratio appeared that the ratio will be great. Okay, and this some factor in front. It appears that now for this model everything negative. So energy will be big and negative, mean energy. But fluctuations are great. We calculated some fluctuations that showed great. And interesting result when we have very fast variation. Very fast variation, it is almost instantaneous jump. Then we have solutions with, in this case, this exact solution. What is interesting that preservation chevron scale gives this condition. You see in the case when omega squared is positive, we had some difference of squares, and here we have imagined part of products of two coefficients. And what will happen here? Again, for the initial Fock state, it appears because the thing is very interesting that final state will be constant, okay, because Hamiltonian is constant now, so energy is preserved. Mean values of coordinate moment are great immensely, but they can cancel each other. So this will have. And if, for instance, this kappa is a model of imaginary frequency, kappa equals omega zero, we have this special case when we have exactly zero mean energy, but with great fluctuations. Okay, and that is formula for great fluctuations. Another problem, okay, this is probability density in this case, and you see formula very interesting that for the first time I met function, but probability density mainly is determined by gamma function of some complex argument, okay, and then it's a hypergeometric function. And this is a picture analogous to the initial ones, now probability density. Again, we have some zeros and some oscillations. And now return to the problem with three parameters. Why it is interesting? Because, for instance, if we calculate instantaneous energy values, this is given by this formula, you see, and you see that this frequency is real even in the non-Hermitian case. If we consider the situation when rho is imaginary, this quantity will be real. This was discovered about 20 years ago. It gave beginning to some very great area, some system with non-Hermitian Hamiltonians. Hamiltonian non-emission, non-Hermitian, but energies, mean energies, or eigenvalues of energies are real. Therefore, we decided to study this system. What happens if initially we have usual oscillator, and then we have time-dependent parameter rho? Okay, I shall, okay, this goes. And it appears that then we shall have some efficient frequency, gamma squared, but immediately we understood that we could add some modulation of the usual frequency. We shall have this. And solutions in terms of parabolic cylinder functions. And it is interesting because parabolic cylinder functions are generalizations of the Hermite polynomials, which are standard for harmonic oscillator. And then we calculated everything, and it appears that it is better to write in terms of confluent hypergeometric function, and we arrived at some explicit expression for this in terms of this complex confluent hypergeometric functions. What is the analytical difficulty? Adiabatic regime means that argument is great and the sum of parameters is great. Therefore, all formulas in books about asymptotics did not help us because in many cases we have this non-stationary regime when the first terms of asymptotic expansions do not help. Even I calculated these first terms and obtained some result that energy must be positive. Sasha showed me that no, energy is negative. So only numeric calculations give correct result. And they give some many interesting results in different regimes. There are regimes when energy increases slowly, another regime when energy becomes negative and decreases rapidly. And some interesting figures, but I shall not comment them. Oh, okay, and what was interesting here, this is the case when we have to take into account these corrections, not only this exponential, but corrections, because these corrections being small, they're responsible for the evolution of energy, exponential function, one coefficient, and this coefficient is some derivatives of these small corrections. So we have exponential changes of energy. And there is some parameter, you see that sign depends sigma more than 1 or less than 1. And this, everything was confirmed. And returning to the non-Hermitian case, it appears that in some sense it's not very interesting because it goes to figures here. For instance, dotted lines, it is a non-Hermitian case, very close to the usual Hermitian case. But what was interesting that how to determine mean values. If we use usual definition that mean values is an integral of psi by psi complex conjugated, these quantities, these integrals are not preserved in time. But how to maintain independence of time? You see that we have really in this case two equations. One equation standard, and another equation when we have a Hermitian conjugated Hamiltonian. And then if we take product psi by psi star, but of another solution, then everything is time independent. We can define these mean values, and the plots are given for this generalized mean value. This is an interesting thing in this non-Hermitian quantum mechanics. From the point of view of mathematics, very nice. From the point of view of applications, I do not know whether they have anything with real life or not. Many people believe that yes, study this, but I do not know. Okay, and finally, a few minutes about this problem with magnetic field. Problem again is reduced to the oscillator with time-dependent frequency. These are solutions obtained for the first time for the constant magnetic field by Fogg and Darwin. He's not that Darwin, but physicist Darwin, although also Charles Galton Darwin. And this is sometimes named the Fogg-Darwin model. And generalizations to the time-dependent situation was given by Malkin, Manko, and Trifodov. The same function, only frequency dependent by this epsilon and frequency and derivative. And generalization of the Born-Fogg theorem, again, very nice figures, distribution over instantaneous Fogg-Darwin states. Figures even more nicer than in the preceding case. And again, we see that, for instance, initial value N25, so the mean energy increases 3 times, must be about 75, but you see half of states is with more energy, half of states with less energy. This case. And now about magnetic moment operator. What happens in this case? Magnetic moment operator must be defined in general case in the following way. If we use the standard definition of magnetic moment integral coordinated by density of current, in the magnetic field density of current contains this additional term related to vector potential, and then we see that magnetic moment operator is proportional to the kinetical angular moment. You see, x multiplied by pi, not by p, this one. And this has consequences because this magnetic moment operator does not commute with Hamiltonian. Therefore, accidentally, in some situations, for instance, in thermal state, magnetic moment is fixed. But if we make some small changes, it becomes oscillating time. So how to obtain the standard adiabatic invariant in magnetic field? Standard adiabatic invariant is ratio of magnetic of Hamiltonian to frequency. But now we have to do double averaging, quantum mechanical averaging over wave functions, and the averaging over some fast oscillations. Then we return to this adiabatic theorem. And about some conclusions. Unsolved problem. Problem unsolved for decades. Try to generalize all this to more general vector potential. You see, parameter alpha. If alpha is 0, that is that model as I discussed now, some named symmetric gauge. Okay, but we have Landau gauge when alpha equals 1. From one point of view, it is simplified because we immediately arrive at the oscillator equation for one coordinate. But for another coordinate, it's just plane wave. Therefore, in this case, we have not only one function, but we have many functions. It was my first scientific work made in 71. And we have a lot of other functions. We have to analyze all of them. Problem is terrible. But more important from my point of view, what will happen if we have arbitrary parameter alpha? What corresponds to arbitrary parameter alpha? You see, let us put solenoid with this cross section, okay? Then, if we calculate magnetic field nearby the center, we shall obtain immediately that general formula where parameter alpha will depend on the ratio of this size of our solenoid. If it's totally symmetric, alpha will be 0, but in general case, not 0. And what will happen in this case when we have evolution, when we did not pass through 0, then this ratio of energy will not depend on the gauge. But if we pass through 0, situation quite different. In this case of alpha equal 1, we can show that, for instance, non-adiabatic evolution. This is circular gauge, this is Landau gauge. Totally different things. And for instance, magnetic moments, for instance, Landau gauge, circular gauge, totally different things. And these are some papers. And a very interesting problem for future studies. I told you, arbitrary alpha, arbitrary form of solenoids, and also problem to take into account effects of dissipation. Because I told you already that standard frequency 50 Hertz, frequency of rotation of electron about gigahertz. And in this case, of course, we have to take into account effects of dissipation. So it is a very interesting problem for young persons who are in this audience who are interested in some new results. I recommend to try to solve these problems. Okay, thank you very much.
We may have time for one quick question from the audience. YouTube?
Professor, you were telling about the frequency some slides ago. May we see it again? So it's the frequency depending on the time.
Frequency depending on time.
Yeah.
Okay, maybe this one.
No, after this, you are exhibiting some frequency, which were the not frequency, the original frequency, minus a term depending on the time square. And I were about to ask you, how do you prevent the frequency to become negative?
I remember that. Okay, you see. It is in magnetic field case. You see, what is the frequency? This is this Larmor frequency. It is magnetic field, okay, charge. And so if magnetic field changes its sign, frequency also changes. If we have harmonic oscillator usually, then it seems that it is something artificial, because in harmonic oscillator we have every time potential energy omega squared. But in the case of particle magnetic field, negative frequency is quite natural. So this is
okay. But the question, the issue was on the other slide. I think it's after this one, maybe 10. 10 slides
Yeah.
after this one.
Here, for instance.
No. It's the knee. It's not omega. It's the knee.
Knee. Yes,
Yeah.
yes, I remember. What will be here?
Close to there.
Now, let.
No, I think.
Yeah, I remember here. Here. You see, this
Yeah,
is
exactly.
parameter
This one.
at this cross term,
Yeah.
and this is knee zero, this initial frequency,
Yeah.
and it can diminish actually this potential energy. Potential energy was positive, then it can diminish until negative values. Then we go to the unstable regime. For instance, how it can happen. For instance, we know that in two-dimensional situation, when we have some traps, we can arrange some potentials on the boundary of traps in such a way that the potential energy will be positive. But changing these potentials in the cathode and anode, we can make it negative. This corresponds exactly to these traps named. It seems to me that Powell trap, this the combination of electrostatic potential and magnetic field. And when we can vary potentials, then it can be negative. Yes.
Nice. I was wondering if you could connect this with antiparticle modes.
No,
this model.
antiparticle I do not know, but it can be done. Yes.
Yeah. Another question. This is much faster, and it's: Do you think this may be applied for some kind of Casimir effect?
About Casimir, it's better to ask Nail.
Thank you, Professor.
No, do not know. No.
Okay, so we now should wrap up this oral session, and we see each other again at the lounge for the poster session and complimentary drinks and coffee break. Thank you very much. Let's thank again Professor Victor Dodonov for this very nice talk. And see you all tomorrow.